So they're distinct copies, and we can see that now with this kind of picture. All right, so what am I actually going to do with foo? So let's see, int b, so this is yet another local variable. B gets n, so now everyone in the world has a value of 5, it seems. So b is 5, n is 5, back over there, a is 5. So b star equals 2, so what's the value of b? So 10, right? So 5 times 2 is 10. So I'm passing 10 into bar. So we're almost done with this story. OK, this was kind of stupid. All bar does is print this. Now, what's the takeaway here? Well, actually, so the takeaway here is, if I had thought about this, we would have been walking through this with GDB. But we did that earlier, so it's not all that enlightening now to step through each of these frames. But if we now get down to bar here, and I print out m is going to be, let's at least close this loop, is going to be 10. Right? We're just not doing anything with it. So actually, we can now do this. Let me go in here, and I'm going to compile this program called bar. So make bar. All right, I'm going to now run GDB on it. So GDB bar /bar, enter. All right, so now I'm going to do a breakpoint at, let's do a breakpoint. Let's not step through this because it gets very boring. Let's do a breakpoint at bar. This is the very last function that ever gets called in this program. So now let's go ahead and do run. OK, so now this is more interesting than last time because we don't have to step through all the tedium with GDB. At this point in the story, I'm kind of pretty deep. That picture is actually starting to stack up. If I type backtrace and hit enter, notice I can see a reminder here what's going on. At the very bottom of my stack is main and its variables. In foo is its variables. In bar is its variables. And again, this is even if you've not yet dabbled in GDB, the goal here really is just to show you some opportunities. I can obviously print out in bar the value of m. Again, m is just this simple thing here, the input. But suppose I get curious in GDB, and I've kind of gone too far, and I actually want to know, wait a minute, what was the value of b inside of the foo function? Right? You might think that, damn, now I have to kind of restart my program, set a new breakpoint in foo. Well, you don't need to do that. Right? We have paused execution by way of a breakpoint. You can see where you've been with backtrace. What's really powerful about GDB is you can kind of go back in time. Or at least, with regard to this picture, you can access any of these frames you want within GDB simply by typing this command. If I'm curious as to what the value of b was in the foo function, even though I'm currently in the bar function, because that's where I set my breakpoint, I can say frame number 1 and hit enter. And voila, it kind of winds back time. It doesn't undo any of the work. It's now showing me what's inside of that frame number 1. So I now can do something like, what was b? And 10. So again, this just hints at, again, the power of something like GDB. You can literally pause execution of your program and go anywhere you want in your memory. And simply understanding the order in which your own functions are getting called will let you begin to traverse this. All right, so let's do one other thing now here. The CS50 library. So in the CS50 library, which we've been taking for granted and will decreasingly actually be using now that we've revealed what a string actually is, a char star, let me scroll down. There's get char, there's get double, there's get float, there's get int, there's get long long, there's get string. Get string is the only one we're going to look at right now, because it actually is used by all of those other functions. When you call getInt, it's actually getting a string from the user and then effectively using a to I, or an equivalent, to convert it to an integer for you. So what is getString doing? I'm going to skip over these local variables here and just reveal a little bit about what's going on. So inside of getString, there's this function that rarely, if ever, you will have to use yourself. But getC, you can kind of guess what it might do. getC, what are we probably getting? It's getting a char, one char at a time. The reason for this is that, as I keep saying, and we'll soon see, it's really easy to overstep, again, the boundaries of your own memory in a programming language like C. And so if you get greedy and you say, give me 10 characters at once, or give me 20, but the user gives you fewer than that or more than that, again, segfault, core dump, crashes, hacking, bad stuff is the takeaway there. So with getC, even though it feels a little less efficient, what getString in the CS50 library is really doing is it's getting one character at a time from the user. And this very paranoid approach to getting input from the keyboard ensures that we never go past what the user has actually typed in. Now, what's really happening here? Well, the way CS50's library works is that initially it arbitrarily allocates a buffer that looks like that, that's size 32. We made an educated guess that typically 32 bytes bytes is plenty for the types of words you guys might type into a program. But just in case that's wrong, and just in case you actually want to type in 33 characters or 100 characters, the getString function needs to be able to grow dynamically. It needs to be able to say to the operating system, we screwed up. We asked for 32 bytes. We actually need 64 bytes. Can we have more? So what the CS50 library actually does, if you read through this, is if we find that, you know what, the so-called buffer, the space we've allocated in getString is too little, turns out there's another function. And this is not something you'll likely need to call, at least during the term, but called realloc, that will do literally that. It will reallocate an array for you and find you more space. And if need be, if you've been allocated here and someone else is already here, what realloc will do is we'll say, all right, you want more memory. I'm going to move your whole array here and put it elsewhere so I can then give you more space so that it all remains contiguous. And so what realloc does, which is nice, is you can't just move an array around in memory. You can't just move bytes from one place to another. But you can do what? You can copy them from one place to another. And so realloc actually does this. So we'll come back to this before long, but know that all this time, the CS50 library has been using malloc and in turn realloc, that's a family of functions, to allocate a chunk of memory. And if it needs more. And now where does getString put that memory that it's handing you when you call getString? Where must the strings from getString be getting put in this memory when they're handed back to you? It's got to be the heap, right? Because if getString foolishly put its memory on the stack, what would obviously happen the moment getString returns? Like that memory, you know, it might still say HELLO in that stack frame, but now, as soon as you call another function, bam, that string's going to get overwritten. So it was important to us at the start of the semester that anytime you allocate a string, that it ends up in the heap so that your functions can get called, finish calling, call, return, and that string stays alive. So all this time, we've actually been using the heap. And we'll see before long yet more sophisticated approaches to that. So let me just give a sense now of why bad things happen so easily. Let me actually skip over the actual code here and focus on this. So if you want to read more about this, especially if you're the Hacker Edition type, this is actually excerpted, this picture, from a Wikipedia article that goes into much more detail. But this is a picture right now of a stack. Right? It's from bottom to top that we keep looking at, but it's got some colors depicted here to make things more friendly. But it turns out that I've kind of been simplifying the world. When I say that on the stack is something like main's parameters and main's local variables and foo's parameters and foo's local variables, there's actually been other stuff still. Long story short, when a function calls another function, the only way that guy, the second guy, knows where he should hand control back to when he's done executing is because what also is going on the stack is each function's return address. In other words, when you call a function, even like printf, this is kind of happening all these weeks behind the scenes. You're essentially writing on a piece of paper your address, your main function's address, your foo function's address, whatever function you wrote. You're handing it to printf and saying, do your thing, and then return to this address, which is my address. So the problem, though, is that this picture then means on top of the stack is a whole bunch of juicy information. Not only are there things like variables. Notice up here there's the variable bar, whatever that is, and the variable c, whatever that is. But these things I just mentioned, particularly this one in red, is a return address. So the return address is that sheet of paper that's been secretly being put on the stack every time you call a function. But here's the bad thing, and here's how this all ties together with arrays. We've said before that an array is a fixed size, and bad things happen if you go too far to the right of your array. But notice what happens. When you're calling functions, notice how this arrow reminds us, the stack grows up, 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 up. But it was someone's bright idea years ago that when you store an array in memory, the first letter, for instance, H, is going to get put here. But then the next one goes there, there, there. And again, this is a picture, so it's not really a rectangle. But then you move down, 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 wrap around, down, down, down. So what happens in this model if the string the user types is not HELLO, but is like 1,000 characters? Where does it go? What memory gets clobbered, so to speak? Well, all of this stuff. So what really sophisticated or lucky bad guys do is they try to, and this can be as simple as running a program at the prompt and typing in some crazy long string and seeing if it crashes. What a bad guy will do is try to inject, let's call it attack code. Just generalize it as A for now. What is an attack code? It can be anything. It can be something stupid like spam everyone in the computer's address book, or it can be erase everything on the hard drive. Attack code is whatever you want it to be. But a bad guy will essentially do this, and the colors here are important. What did the red colors represent? The return address, that sheet of paper. So a really smart bad guy will somehow figure out, to be honest, quite often by trial and error, a whole lot of trials and a whole lot of errors, but it only takes one success to then break into the system. He or she will try to figure out, where is this address? Where is that sheet of paper being stored in this program? Because I'm going to type in some crazy long sequence of characters, and it might not even be alphabetical ASCII characters. It can be like those unprintable characters where it looks weird on the screen because it's just zeros and ones. I'm going to inject some kind of crazy long string, attack, 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 but I just have to get one detail right. The very last thing I type in at the keyboard or pass to the server via the internet, say via URL, has to be the address of my own attack code. So if what you do when prompted by something like getString is you type in the equivalent on your keyboard of an attack function that, again, deletes something, sends spam, whatever, but you get the very last detail right and you say, the address of my own attack code is going to start at this address, 80C0, whatever that is. So long as you put that address, 8035C080, to refer back to you, what's going to happen? Whatever function this is, printf, getString, or whatnot, he's going to finish executing. He's going to say, all right, I've been told to return to this address, but what just happened? Someone else wrote over what I wrote on this, thereby telling me to return to a different return address, and that return address is depicted in A there, and that might literally mean go erase the hard drive now. So how do bad guys figure this out? It really is a lot of trial and error. Anytime you visit a website, anytime you run a program and it crashes, it core dumps, you get file not found or an internal server error occurred, this is prime hacking opportunities for bad guys because what it suggests is not necessarily that there's a vulnerability, but there's at least a mistake. Someone screwed up and did not check the length of an array. Someone let me go too far in memory. And so if I can actually now guess by trial and error, writing a program that generates a whole bunch of garbage, just seeing which one actually gets me into the system. This is incredibly common how bad guys get into systems. And in fact, if you ever run a web server, as you might do for your final project, and troll through your own web logs, you'll see that there are these people called script kiddies on the internet who essentially run programs like this, sometimes not even knowing who you are or caring who you are, but trying to send garbage values to your web server in particular. And so you'll see crazy long URLs show up in your log because it's been incredibly common that web servers on Linux, on Windows, on Mac OS actually have flaws like this, where if you get that input just right, you can trick the computer into doing anything you want. Whew. So with that said, we'll see you on Wednesday. What's up?